This tutorial deals with problem solving in titrations. Now, we can have several different types of titrations. There are acid-base titrations. We can have complexometric titrations. And one other example of titrations would be redox titrations. But no matter what type of titration we're dealing with, the problem solving is essentially the same and is remarkably straightforward if we understand the basics of what a titration is all about and we pay attention to some key details regarding the chemistry of the titration. Now, one last thing before we get underway. This method of problem solving doesn't use dimensional analysis in the way that it was used in the tutorials on the gravimetric analysis experiment. But I'm showing it here as a method which is an alternative to dimensional analysis in problems involving titrations. The example or examples given at the end of this tutorial will use this alternate method and contrast it with taking a dimensional analysis type approach. You can use whichever method you're most comfortable with, provided that you show all your calculations in a neat and orderly manner. So let's begin here with what a titration is all about. So in a titration, we would have an aqueous solution of a chemical in an Erlenmeyer flask. So here is the Erlenmeyer flask, and let's say that the chemical in here is chemical A, and it's in aqueous solution. Now we would add to this Erlenmeyer flask a measured volume of solution A, and the volume is, for practical purposes, would be measured in milliliters most of the time. So let's call that VA, the volume of solution A. Now the solution has a concentration, so the concentration most often used is in units of moles per liter. So we would call that the molarity, concentration in moles per liter of solution A, and we'll call it MA. Now a burette would be loaded with another solution, let's say solution B, an aqueous solution of chemical B, and the concentration of this solution in moles per liter we'll call MB, the molarity of solution B. And what we normally do in a titration is, having added a measured volume of solution A to the Erlenmeyer flask, we would add solution B to the Erlenmeyer flask so that chemical B reacts with chemical A, and we would continue adding from the burette until we have added just enough of chemical B to react with all of chemical A that was originally present. So by recording the reading of the burette before and after delivery, we obtain the precise volume of solution B needed to react with chemical A that was originally present in the Erlenmeyer flask. And this is referred to as the titer or the titer figure. So we determine through titration the volume of solution B in this case in units of milliliters, and we'll refer to that as VB. So there are essentially four quantities that we're dealing with in any titration. First of all, the concentration of the solution in the burette and the volume obtained from the burette of this same solution needed to react completely with the chemical in the Erlenmeyer flask. The next quantity is the initial volume of the solution A added to the Erlenmeyer flask, and the fourth quantity would be the concentration of solution A. And when solving problems involving titrations, we always know three of these four quantities. Only one of these quantities is unknown, and we can solve for that. For example, we may know these three values here, and if we know these three values, we can solve for that value. So again, in titrations, we always know three of these four values, and we have to solve for the unknown value. Now, before we go any further, we should be very clear on how we can convert between concentration or molarity, as we use in most titrations, how we can convert between molarity, volume, units of volume, and moles. We need to be clear on how we can convert between those three. Now, the units of molarity are moles per litre. Units of volume are litres. And if we multiply molarity by volume, we are in fact multiplying moles per litre by litres, and the litres will cancel, and that will give us moles. So, molarity times volume equals moles. We must remember that. Molarity times volume equals moles. Now, another important thing for us to know when we're problem solving in titrations is the balanced chemical equation. So we need to know the stoichiometry. We need to know the stoichiometry of the reaction, or at least we need to know the relative numbers of moles of reactants. So we must always write out the balanced chemical equation for the reaction involved in the titration. So let's say this here is the balanced equation. Reactant A plus reactant B forming whatever the products might be. So if this were the balanced chemical equation, the stoichiometry of the equation is therefore 1 to 1, meaning 1 mole of A will react with 1 mole of B. Now, I'm just going to use another 2 examples of different stoichiometries. So let's say this here is the balanced chemical equation. 2A plus B forms products. So in this case, if this were the balanced equation, the stoichiometry is 2 to 1. 2 moles of A will react with 1 mole of B. And another example we'll use is this here, A plus 2B forming whatever products are formed. So again, if this were a balanced chemical equation, the stoichiometry is 1 to 2. So for every 1 mole of A we have, we need 2 moles of B to completely react with it. Now there are many other possibilities in stoichiometry. For example, 3 moles of A plus 2 moles of B could be 3 to 2 relationship, but I'm just going to use 3 examples here. Now let's focus now on the stoichiometry being 1 to 1. So if the stoichiometry is 1 to 1, we can say that the moles of A originally present is equal to the moles of B needed to completely react with it. If we look up here, if a certain number of moles of A are originally present in the Erlenmeyer flask, then if the stoichiometry is 1 to 1, we're going to need the same number of moles of B to completely react with A. So moles of A are equal to moles of B. So remembering our relationship between moles, molarity, and volume, remember moles is equal to molarity times volume. So getting back to the moles of A here, the moles of A will be equal to the molarity of A times the volume of A. And that will be equal to the moles of B, which will be the molarity of B times the volume of B. Now looking over here where the stoichiometry is 2 to 1, we can say, with respect to the moles, we can say that the moles of A is equal to 2 times the moles of B. In other words, if you have 1 mole of B, you need twice that number of moles of A. So again, number of moles equals molarity times volume. So we can say that the molarity of A times the volume of A equals 2 times the molarity of B times the volume of B. And lastly, looking at this example where the stoichiometry is 1 to 2, for every 1 mole of A, we need 2 moles of B, we can say that 2 times the moles of A equals the number of moles of B. In other words, for every 1 mole of A, we need twice that number of moles of B. So, relating this again to moles equals molarity times volume, we can say 2 times the molarity of A times the volume of A equals the molarity of B times the volume of B. And so we can see the stoichiometry of the reaction, which tells us the relative numbers of moles of A and B that are reacting, allows us then to come up with the equation here, which relates moles of each species to the molarity and the volume of the solution of that species. And remember, in any titration problem, we will always know 3 of these 4 values, MA, VA, MB, VB. So let's say we knew the values of MA, VA, and MB, and VB was unknown, then we can solve for VB by rearranging this equation here. VB will be equal to the molarity of A times the volume of A divided by the molarity of B. And let's just take another example. Let's say we did not know the value of the molarity of B, and we knew VB, VA, MA. We can solve for the molarity of B by rearranging this equation. The molarity of B would be equal to the molarity of A times the volume of A divided by 2 times the volume of B. And then just to finish off on this third example here where the stoichiometry is 1 to 2, let's say we did not know the volume of A, then we can solve for that again by rearranging this equation. The volume of A would then be equal to the molarity of B times the volume of B divided by 2 times the molarity of A. Okay, so to summarize problem solving in titrations, there are really 3 main steps that we need to take care of when doing these problems. So first of all, always write down the balanced chemical equation. So write out the balanced equation. You know, whether it's A plus B going to products, showing the stoichiometry of the reaction. So this will confirm the stoichiometry. And that's the stoichiometry with respect to the reactants, whether it's 1 to 1 or whether it's 2 to 1 or 1 to 2 or whatever. Secondly, you should state the moles of one of the reactants in terms of the moles of the other. State the moles of A in terms of the moles of B. So if the relationship was 1 to 1, the moles of A would be equal to the moles of B, and then converting that to molarity times volume, we would say MA VA equals MB VB. If the stoichiometry was 2 to 1, then the moles of A would be equal to 2 times the moles of B, and we would come up with the relationship MA VA equals 2 MB VB. So state the moles of A in terms of the moles of B to come up with the MA VA MB VB equation. And thirdly, using the 3 known values, solve for the 1 unknown value using the equation. Okay, so that just about does it for problem solving in titrations, and maybe we should go over a couple of examples now. So let's clear this and bring up a sample problem. And in fact, I think we're just going to have time to do one sample problem here because this tutorial is already getting a little bit lengthy. So here we have a titration that took 23.46 milliliters of sodium hydroxide solution to neutralize 25 milliliters of 0.05218 mole per liter sulfuric acid solution. So what we have to determine is the concentration in units of moles per liter of the sodium hydroxide solution. Now, I prepared ahead a little bit here just to save some time. So we're going to take a look at the alternate method that we've just gone over in solving this problem, and we're going to contrast that with the dimensional analysis type approach to the same problem. So looking at this diagram here, as we try to get a clearer picture of what's happening in this titration. So here we have the sulfuric acid in the Erlenmeyer flask, and the concentration of the sulfuric acid is given as 0.05218 moles per liter. So we can call that the molarity of the sulfuric acid, H2SO4. What else do we know about the sulfuric acid? Well, we know that we titrated a 25.00 mil sample of the acid solution. So we can call that the volume, or V, H2SO4. And we also know that in the burette we had the sodium hydroxide solution. And what do we know about the sodium hydroxide? Well, we know that the volume was 23.46 milliliters. That was the tighter figure in the titration. The volume of sodium hydroxide needed to neutralize 25 milliliters of this sulfuric acid solution. So the volume is 23.46 milliliters. We can call that V sodium hydroxide. The only thing we don't know here is the molarity of the sodium hydroxide. That is what is unknown, and that's what we have to find. So again, as we described earlier, of these four quantities, one is unknown, and we're going to have to solve for that. So as always, we begin by writing out the balanced chemical equation for the reaction. So we have sulfuric acid reacting with the sodium hydroxide, and the products will be the salt, the Na2SO4, sodium sulfate, and water. Now, we've not yet balanced this reaction. To maintain two atoms of sodium, we need two here, and we need two here to balance the equation. So now the equation is balanced, and we can see the stoichiometry of the reaction. Stoichiometry is 1 to 2. So for every 1 mole of sulfuric acid that we have, we need 2 moles of sodium hydroxide to completely react with it, to completely neutralize it. In other words, we can say 2 times the moles of sulfuric acid is equal to the moles of sodium hydroxide. Therefore, we can come up with the equation 2 times the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. Remember, molarity times volume equals number of moles. So substituting in our known values to this equation, we get 2 times the molarity of the sulfuric acid, 2 times 0.05218 moles per liter, times 0.02500 liters, that's the volume of sulfuric acid that was used, is equal to the molarity of the base times the volume of the base, the titer figure, which is 0.02346 litres. So by rearranging the equation here, we can solve for the unknown quantity, the molarity of the base. So the molarity of the base, of the sodium hydroxide, is equal to 2 times 0.05218 times 0.02500 divided by 0.02346. And if we do that, we get a result of 0.1112 moles per litre of sodium hydroxide. And we need to use 4 significant figures in the final result here. Now, using a dimensional analysis approach here, again, we will write out the balanced chemical equation, H2SO4 plus 2 NaOH, producing sodium sulfate, Na2SO4 plus 2 H2O. And of course, as always, we get from that the stoichiometry of the reaction, as before, is 1 to 2. So as is always the case in the dimensional analysis approach to these types of problems, titrations, we have to determine the number of moles of one of the reactants and then convert that to moles of the other reactant via the stoichiometry of the reaction. So we have to determine, given the information available in the problem, can we determine the number of moles of the sulfuric acid present, or can we determine the number of moles of the sodium hydroxide present? And if you look at the problem, we can figure out that yes, we can determine the number of moles of sulfuric acid present from the information given in the problem, but we cannot yet determine the number of moles of sodium hydroxide. So we'll have to determine, first of all, the moles of sulfuric acid present, and then convert that through the stoichiometry 1 to 2 to the moles of sodium hydroxide present. So we can first convert to moles of sulfuric acid. So knowing the molarity of the sulfuric acid, 0.05218 moles per litre of sulfuric acid. If we multiply that by the volume of sulfuric acid, which is 0.02500 litres of sulfuric acid, we'll see that the litres of sulfuric acid will cancel out and leave us with moles of sulfuric acid. And now we can convert to moles of sodium hydroxide through the stoichiometry of the reaction. So we multiply this by the stoichiometric ratio, which is 2 moles of sodium hydroxide per 1 mole of sulfuric acid. We then get the moles of sulfuric acid to cancel and leave us with moles of sodium hydroxide. And the last step in the calculation is to convert that from moles of sodium hydroxide to moles per litre using the titer, the volume of sodium hydroxide that was used. So we multiply, in this case, by 1 over the volume of sodium hydroxide in units of litres, which is 0.02346 litres. And if we calculate all that out, we get a result of 0.1112 moles per litre of sodium hydroxide. Again, this final result is reported to 4 significant figures. So that'll just about do it for problem solving in titrations. And remember, you can use any method of calculation that you like, the dimensional analysis approach or any alternate method. But do remember when you are performing your calculations to show them clearly and neatly. Now we're not going to show any more sample problems in this tutorial. This tutorial has gone on long enough, but we will tackle one or two or maybe even three of the problems in this study guide of your lab manual in another tutorial. Thank you for watching.